Hey everyone, welcome to Database Fundamentals. So today we're going to talk about one of the core concepts in relational databases, functional dependencies. In today's video, I will walk you through how understanding functional dependencies can dramatically improve your database design. Let's first begin with why functional dependencies matter. A lot of times when we have poor schema design, it leads to redundancy as well as data anomaly. There are three common data anomalies. Update anomalies is basically saying that the same information is stored multiple places, and every time we change it, we need to change it everywhere. And delete anomalies and insert anomalies, we'll talk more about them. So these anomalies can cause inconsistency of the data. When the data is not agreeing with itself, it's not just a matter of bad data, it's the matter of bad database design. So in this lecture, we'll talk about how we can use functional dependency to avoid these problems. So first, we're going to look at a example. So this is a common scenario. This is a table about university course management. So we got a table of student ID, student name, course ID, course name, and room, and instructor ID, instructor name. So if you know how to write a SQL, if I ask you to write some query using this table, it will be fairly easy to do so because everything is stored in this giant table. So it looks pretty convenient, but it's actually very problematic. We'll use this example to walk through the different types of anomalies. So the root problem of this table is that different information are stored in the same place. And the first issue we could encounter is that suppose Dr. Smith needs to change his name, and we now need to update every record where Dr. Smith appears, because for every student enrollment record, we're storing the instructor name. Basically, we're storing the same piece of information multiple times. And if we need to change it, we need to change it multiple times as well. And if you don't change it everywhere, then the data becomes inconsistent, as we have discussed before. This is happening because the same data is redundantly stored, and the solution lies in functional dependencies. It is because the instructor ID should determine instructor name, and hence it is introducing some redundancy in this table. So this is called update anomaly. And then we're going to look at what is delete anomaly. So as you can see that the storing the information about the courses as well as the instructors depend on storing some student enrollment information because of the way the database is constructed. So if the last student drops out from the course, then we lose not just enrollment information, but all of the data about course information and instructor information. So this shows that important data is only indirectly preserved, and this is a consequence of ignoring functional dependency. So ideally we should have course information to be stored in a course table, and then instructor information to be stored in an instructor table, and they should not really depend on whether there are student enrollments at this time. And there's also on the flip side, there's also insert anomaly. So let's say I create a new course, and this course has a course ID of CS410, and the course name is machine learning. It's a very popular course, and it will be taught in room R130, and the instructor is Dr. Lee with an ID of I003. So the thing is that what if nobody enroll in this course? So it is kind of like the situation in delete anomaly. So in this case, I cannot really record this information unless a student is enrolled. So the schema is not allowing me to insert a row in here where the student ID is empty or the student name is empty. So this is the case where we have insert anomaly. So what exactly is a functional dependency? Now we need to look at the formal definition of a functional dependency. Formally, if two tuples agree on X, they must agree on Y. So this is basically what functional dependency is saying. And X is a set of attributes in the relation R, and Y is also another set of attributes in the relation R. So if X determines Y, then what it implies is that if for any two tuples that agree on X, they must also agree on Y. So this is an example. For example, student ID functionally determines student name, and it's basically saying that every student has exactly one name. So if we have two rows where the student IDs are the same, then we know that the student ID is a unique identifier of the student and their names should also be the same. So basically, based on this functional dependency, we know that we're looking at the same student, so they have the same name. How do we identify functional dependencies? Well, from these tables where the attributes are real-world attributes, we can basically infer these functional dependencies based on their semantics. Because a lot of times, if a attribute or a set of attributes is a primary key of the table, then it is a unique identifier, in which case it should functionally determine every other attributes. And in this case, if we're looking at students, if we know that the student ID is a unique identifier of the students, then we know that student ID should functionally determine student name. So basically, for every two tuple where the student ID are the same, we should expect the student names to be the same as well. To fix anomalies, we can do normalization. This means we need to split the original big table into smaller ones, each based on the functional dependency. Now, updates and deletions are safe, and you can insert standalone data. So with normalization, we will be able to have a clean, robust design with minimal redundancy. So this is an example of how we can normalize the bigger table into smaller ones. So the original table is now decomposed into 4 tables. We got the student table storing only student information. We got instructors and courses storing instructor information as well as courses information. And then we have a enrollment table that records the interaction between the students as well as the courses. So let's take a step back and really understand whether these anomalies are addressed in this new schema. So what about update anomaly? What if Dr. Smith? What if the instructor ID, this person changes his name? Now he is called Dr. Jerry. So in that case, we don't have update anomalies anymore because this information is only stored in one place in the instructor table. So we only need to change it here, and in this case, we won't have update anomalies. And for delete anomalies, if because we're storing course information in the course table, we're storing instructor information in the instructor table. If the last student drops out from the course, then it doesn't really affect our data about the instructor or the courses. And in the same way, if we make a new course like machine learning and nobody is enrolled in this course, it's fine because we're storing course information in the course table, and it is completely okay and completely acceptable for the new schema to not have any students enrolled in the new course. So now we can see that the new relational design is preventing those anomalies. And in the future lectures, we will talk about a systematic way of decomposing a big table into smaller tables. So that is called normalization. And we will talk about a bunch of normal forms and how we can achieve those normal forms via normalization. So in the previous slides, we talked about we could kind of infer the functional dependencies based on the semantics, and a lot of times the functional dependencies are specified by the database manager. How can we get more functional dependencies based on the existing ones? So we can use Armstrong's axioms. So the first three axioms are the most important ones. So basically the first one is saying that if y is a subset of x, then x should functionally determine y. And the second one is saying that if x is functionally determining y, then xz is determining yz. And the last one, transitivity, if x determines y, y determines z, and then we should have x determines z. So these three rules are the most important ones, and we can also derive other rules based on these rules. Let's take a look at more examples of functional dependency. So this is an example from a bookstore database, and in this bookstore database we have the ISBN number determining the title, author, publisher, price, and the category. And so most likely the ISBN is a unique identifier of the books, and the publisher is determining publisher phone, and the author is determining author email. And we can also have such functional dependencies in the hospital management database. So we could have patient ID determining patient name, doctor ID determining doctor name, and the combination of patient and doctor to determine the treatment of this specific patient. And to wrap up, functional dependencies let us design clean schemas, avoid anomalies, and understand keys. So in the next lectures, we will talk about how we can use functional dependencies to compute candidate keys, and we will also explore different normal forms, the second normal form, the third normal form, and Boyce-Codd normal forms using functional dependency.